if your answer to question 3, give me 2 reasons why a group of integers mod 6, so Z6, is not the same as the dihedral group of the triangle D3. If your answer includes a statement like the elements are different or the operations are different, my caution to you is you are being hoodwinked. Remember, we care about differences that matter, not differences that do not matter. We care about abstract algebra differences, not concrete algebra differences. I don't care that one of these is numbers and the other one is symmetries. I don't care that one of them has addition and the other one has function composition. I care about the structure. Right? What properties does that operation have? What properties do the elements in these groups have with respect to one another, not with respect to some concrete frame of reference of concrete algebra? So the exercise I asked you to think about the most on this sheet was to figure out at least 2 really good reasons, abstract algebra reasons, not concrete algebra reasons, for why the group of integers with operation addition mod 6, so 0, 1, 2, 3, 4, 5, and the operation is addition mod 6, and the group of symmetries of an equilateral triangle, I, T, R, squared, R squared, with the operation of function composition. This is the dihedral group of the triangle. Why? Give me 2 reasons why those are different, fundamentally different groups from an abstract algebra perspective. So some team, I have to call you all teams because groups are these things, your teams. So some team, give me 1 reason why these 2 groups are different. Yeah, Kelly.
The group of integers 6 has orders. One of the elements has order 6, and in the dihedral group of triangles, none of the elements have order 6.
Great. One of the things that we said in our last class about sameness and difference between groups is that if 2 groups are in fact quote unquote the same, it means that all their elements, for every element of a given order in one group, we should be able to find an element of that same order in the other group. But Z6, the group of integers with addition mod 6, has an element of order 6, while D3, how did you know, by the way, that D3 does not have an element of order 6? How did you figure that out?
I looked at the element. I looked at the order of each element, and I only got 1, 2, 3.
Yeah, you can be super, these are small enough groups so we can be super specific. We can find what are the orders of these elements. And if we did that for Z6, we'd find that the orders are 1, 6, 3, 2, 3, 6. And for D3, it's 1, the way that I've listed them, 1, 2, 3, 2, 3, 2. I think I have those all right. So yeah, you look into Z mod 6 and you find that there's an element of order 6. What is an example of an element of order 6 in Z6? 1. Also 5, right? And so coming back to a conversation I had with this group over here, the fact that there's an element of order 6 in Z6 actually also tells me something else about that group. It's a cyclic group. Now, why is that? Why does knowing that there's an element of order 6 in Z6 tell me that Z6 is a cyclic group? What does cyclic even mean? Yeah.
1 or 5 can produce any of the other.
Exactly. So this is our first time meeting the definition of cyclic group during class, but this is a big takeaway. Either 1 or 5. If I take high enough powers of 1 or 5, powers mean iteratively adding it to itself, right? That those elements can generate every other element in the group. And so we would say 1 is a generator, because if I add 1 to itself, I come up with 2. If I add another 1 to that, I get 3. If I add another 1, I get 4. If I add another 1, I get 5. If I add another 1 to 5, what do I get? 0, because we're adding mod 6. So adding 1 to itself repeatedly will get me all of the elements in Z mod 6. What about 5? 5 plus 5 is going to give me 4 mod 6. Add 5 again, and I get 3. What's the mental shortcut here, by the way? What is 5 the same as mod 6 in the integers? -1. So another way to think about why 5 is also a generator is it's just the opposite. It's the additive inverse of the generator 1. So if I add 5 to itself repeatedly, I will also come up with all of the elements. Now, of course, a group is cyclic as soon as we know that 1 generator exists. But in this example, there seem to be 2 different possibilities for a generator. And a good question for any cyclic group, this is a question I'm going to put off to the side because we're going to answer it, I think, in our next chapter. How many generators can a cyclic group have? This particular cyclic group has 2, but what's this question look like in general? So that's one that we'll put on the parking lot here. Okay. But now that we've made that observation, the fact that there's an element of order 6 and the group has order 6 means that my group is cyclic. That actually surfaces a second good reason why these groups are not the same. What is it? Suppose that we believe D3 is not a cyclic group, in which case this is a legitimate disagreement in the abstract structure between these two groups. How do we know that D3 is not cyclic? Now, the first blush that I heard from your groups when I asked you this question, if you were talking about this, is you said things like, well, we can't somehow generate a rotation, an R, by taking powers of T, the reflection. Right? I can't arrive at a rotation just by reflecting a bunch of times, because as soon as I reflect twice, where do I end up? Back at the identity. Same thing, I can't generate the reflection using rotations, because one power of R is going to give me R, another power is going to give me R squared, and another power is going to take me back to identity. So on its face, it seems like that rotations and reflections are different enough that we can't use one of them to generate the other, and so we won't have a cyclic group. But that is a, what would we call that? Mathematicians call that a hand-waving argument. It's not quite a proof, but it has the ring of proof to it, right? Is there another way to understand why D3 is not cyclic? I've actually kind of got it sneakily written up on the screen here. What else do we know about every cyclic group?
There's a generator.
Every cyclic group, by definition, has a generator. Maybe more than one generator, but it has to have a generator. What else? What other property does every cyclic group have? Every cyclic group is also an abelian group. Remind me, what does abelian mean? Commutative property is satisfied by its operation. Right? Every cyclic group is also an abelian group. So what does that tell me about, well, what does that tell me about this assertion? D3 is not cyclic. How could I prove that D3 is not cyclic?
By showing it's not abelian.
By showing it's not abelian, the contrapositive of the statement that's up there. And that feels like an easier thing to verify than verifying that D3 is not cyclic. How can I prove that D3 is not abelian?
Show that it's not commutative.
Show that the commutative property is not satisfied. How many counterexamples to the commutative law do I need? One. What's a good one? What is a counterexample that shows that the commutative property is not satisfied?
TR equals RT.
TR versus RT. How do we know that those two are not the same? Well, we could pull up the Scratch geometry app that I made and just verify. Or another way to do it is to remember, in the dihedral group, what in fact is RT equal to?
TR squared.
TR squared in this example for the triangle. In general, it's TR inverse, right, for any dihedral group, but R inverse is the same as R squared in our group. So D3 is not abelian, and therefore it cannot be cyclic, because every cyclic group is an abelian group. By the way, this theorem up here, G is cyclic implies G is abelian, this is like every abstract algebra teacher's favorite thing to assign students to prove. Because this is the kind of proof that once you unpack the definitions of cyclic and abelian, your napkin version of this proof is going to be very simple. Then actually writing that up into a narrative is a good exercise. So something to maybe add to your to-do list for the weekend is see if you can flesh out that proof. That if G is a cyclic group, then G is an abelian group.